Okay, we're going to talk about nuclear chemistry. Just a point for you to remember. Let's talk a moment about the nucleus of an atom. Okay. Remember that this is called an isotopic symbol, and we include the mass number, which is the number of protons plus neutrons, in the upper left. The atomic number, which is on the periodic table, is in the lower left, and that tells you the number of protons. If it's neutral, it is also the number of electrons. The symbol of the element, hopefully that's self-explanatory. Please remember that the mass number is not on the periodic table. That decimal number is the atomic mass. So, the protons and neutrons are located in the nucleus. They are called nucleons. Again, the number of protons is the atomic number, and that the mass of the protons and neutrons is effectively the mass of the atom, because electrons are 1/2000th the mass of a proton or neutron. So what is known as the nuclear charge? How are nuclear reactions used in our everyday lives? And what is different about this type of chemical reaction? Because so far we've only talked about what we call ordinary chemical reactions. And the ordinary chemical reactions are just with the electrons. Okay, so ordinary chemical reactions just involve the electrons. We're going to start talking about nuclear, which is the protons and neutrons. So just a definition, isotope. Not all of the atoms of the same element have the same mass, because hopefully you remember the discussion about isotopes. These are atoms of the same element that differ in the number of neutrons. As an example, uranium. There's uranium-234, 235, and 238. All of these are isotopes naturally occurring for uranium. So, what causes something to be radioactive? And it's not uncommon for some nuclides of an element to be unstable, okay, or radioactive. Those are referred to as radionuclides, and there are several ways that there are several nuclear reactions that cause an atom's nucleus to split and form more stable nuclides. And that's called decaying. Okay, so terms to note: nuclide, nucleus with a specified number of protons. A radionuclide is a radioactive nuclei. Radioisotopes are atoms that contain radionuclides. Another definition, oops, thought I was going to switch. Another definition for this radioisotope is, and this might make a little bit more sense. Okay, a radioisotope has an unstable nucleus. Okay, and that unstable nucleus is going to emit radiation during its decay to a more stable form. So just like in all of chemistry, these things are going to do something to become more stable. Let's take a moment and talk about what is in this nucleus. It's neutrons and protons. And remember, protons are positive, neutrons are neutral. Since every element except hydrogen has more than one proton, those protons are repulsed by each other. So you've got some repulsive forces in the nucleus. there's something called a strong nuclear force, okay, and that keeps the nucleus from flying apart. So there's some attractive force that's greater than that repulsive force holding these nucleons together in the nucleus. As it turns out, these neutral, you can look at the neutrons as being kind of a buffer between those positively charged protons in the nucleus, and they add a stabilizing effect to the nucleus and allows that nucleus to stay together. We can look at a graph of neutrons versus the number of protons in an element or in an atom. And this is going to give us some indication of the stability of that nucleus. If I have an atomic number, remember Z is atomic number, okay, equal to the number of protons. If Z is less than 20, okay, you can see that the stable nuclei have a 1-to-1 ratio, right? If you look at this graph, the important thing to note here is something called a belt of stability. Isotopes that are in that belt of stability are stable. Okay. Isotopes that are outside of that belt of stability are going to react nuclearly to get to that belt of stability. Okay. But if you notice, that belt of stability for elements with 20 or less protons is about a 1-to-1 neutron to proton ratio. Okay. As the nuclei get larger, it takes a greater number of neutrons to stabilize that particular nucleus. And that belt of stability, again, shows us what those ratios are. I will have to post that video later. Okay, but radionuclides, radioactive nuclides, spontaneously emit particles and electromagnetic radiation when they react to form stable particles. The first type of radioactive decay is called alpha decay. This is when a radioactive isotope emits what's called an alpha particle to become more stable. An alpha particle is a helium nucleus. Helium nucleus. So that means 2 protons and 2 electrons. Notice that this is the way the alpha particle is drawn. There is no charge on it, even though the charge of an alpha particle is a +2. Okay, 2 plus. If you notice in this reaction that there is some type of conservation. On my reactant side, my atomic number for uranium is 92. Atomic number for thorium plus that alpha particle equals 92. The mass number is 238. The mass number for both thorium and that alpha particle also add up to 238. And you do have to conserve those numbers when you are drawing radioactive reactions. I should say nuclear reactions. The second type, oops, my goodness. The second type we're going to talk about is beta decay. Beta decay is the loss of a beta particle. A beta particle is a high energy electron. It can be drawn, or the symbol is one of 2 things, either fancy B or a symbol for an electron. Okay. Notice that the mass number is 0 because there are no neutrons and no protons. It is an electron. Okay. So for example, if I have the decay of iodine through beta decay, I form xenon and an electron. Again, look at the numbers. 54 and a negative 1 gives me 53, which is equal to that. And then 131 and 0 is again equal to that. Another form of nuclear decay is called a positron emission. A positron is a particle that has the same mass as an electron, but an opposite charge to that electron. Okay? So a positron is kind of like a proton, but without the mass. Okay? We draw it this way. Notice that the charge on that kind of electron-looking symbol is a positive, because this is a positron. Again, noting the equation, 5 and 1 equals that, and 11 and 0 equals that mass number of the carbon 11 isotope. You should, at this point, know what an alpha particle is. You should know what a beta particle is. You should know what a positron is. And you should be able to write equations for an element given the type of decay that it undergoes. In addition to the alpha, beta, and positron, there is a gamma emission. Okay, gamma ray, that hopefully might sound familiar, is really just a high energy radiation that accompanies the loss of a nuclear particle. So you almost always get some kind of energy emitted in the form of gamma rays whenever there is a nuclear decay. Another type of nuclear decay is called electron capture, also known as K capture. And this is pretty much what it sounds like. This is the kind of the nucleus of a isotope, grabs an electron from an inner energy level, and that electron combines with a proton to form a neutron. Okay, so in summary, the types of radioactive decay are alpha decay, beta decay, positron emission, gamma emission, and electron capture. That'll be it for this screencast. The next screencast will include more talk about the stability and half-lives.